Hi, today we are going to discuss about measurement of Q factor. So Q factor is known as quality factor or Q factor. Is defined as a dimensional parameter that describes the underdamped condition of an oscillator or resonator. The quality factor measures the performance of a coil, a capacitor or an inductor in terms of its losses and resonator bandwidth. So the definition of a quality factor was originally envisaged by an engineer called K.S. Johnson of the US Department of Engineering of the Western Electric Company. He measured the efficiency and consistency of the various coils. During his studies, he developed the idea of the Q factor. Curiously, his option of letter Q was made not because of the word quality factor used since all the other letters of the alphabet were taken. So the Q factor implies energy losses within a resonant device that might be anything from a mechanical pendulum, an entity in a mechanical structure, or from an electrical circuit such as a resonant circuit. So Q factor shows the energy loss due to the quantity of energy contained in the design. Thus the larger the Q factor, the lower the rate of energy loss, and hence the slower the oscillations. They are going to get a lower degree of damping and they are going to ring longer. So in the case of electronic circuits, energy losses are caused by resistance inside the circuit. While this may occur somewhere within the circuit, the main trigger of the resistance is inside the inductor. Also, the Q factor of the element corresponds to losses. It relates directly to the bandwidth of the resonator with regard to its center frequency. And it is how to measure the Q factor. So the instrument used to calculate the quality factor of the radio frequency circuit is called the Q meter. So the Q meter calculates the quality factor of the circuit and indicates the total energy dissipated by the circuit. So it also describes the characteristics of the coil and the capacitor. The Q meter is used in a laboratory to measure the radio frequency of the coils. So the working principle of the Q meter is a series resonance. So resonance is the state that occurs in the circuit when their inductance and capacitance are of equal magnitude. They cause energy that oscillates between the electrical and the magnetic fields of the capacitor and the inductor. The Q meter works based on the characteristics of the resistance, inductance, capacitance of the resonance series circuit. So at this resonance XL equal to XC or EL equal to IL XL and EC equal to IXC and E equal to IR. Or the Q factor is given as Q equal to XL divided by R or XC divided by R or EC divided by E. So from the equation E is kept as constant, the voltage across the capacitor can be estimated by a voltmeter calibrated to read directly in terms of Q. So the quality factor of the resonator can be characterized as the frequency of the resonator divided by the bandwidth of the resonator. So Q is calculated by using the formula resonant frequency divided by bandwidth, where the resonant frequency and bandwidth must be given in the same units. The Q factor formula differs for each type of circuit. Discussed below are few Q factor formula for various electrical circuits. So Q factor for inductor. So the quality factor of the specific reactive component depends on the frequency at which it is tested. This is usually the resonant frequency of the circuit in which it is included. So the quality factor of a resonant circuit using the inductor that includes its series, loss and a perfect capacitor is used to determine the Q factor of an inductor with a series loss resistance. So the quality factor of an inductor is given as QL equal to XL divided by RL or omega naught L divided by RL. So the omega naught is the resonant frequency in radians per second, L is the inductance and XL is the inductive reactance and RL is the series resistance of the inductor. Next, Q factor of the capacitor. The Q factor of a capacitor with a series loss resistance is the alike as the Q factor of a resonant circuit utilizing that capacitor with a perfect inductor. The Q factor of the capacitor is given as QC equal to minus XC divided by RC or 1 divided by omega naught C into RC. Here, omega naught is the resonant frequency in radians per second C is the capacitance, X is the inductive reactance, and RC is the series resistance of the capacitor. In general, the Q factor of a resonator, including a series sequence of a capacitor and an inductor, can be resolved from the Q factor value of the components. This is applicable to whether their losses arises from series resistance or differently. So the Q value is of the capacitor Q equal to 1 divided by 1 by QL plus 1 by QC. And the Q vector of LC circuits. So L is the inductor and C is the capacitor. So in the parallel LC circuit, the resistance R of the inductor is in series with the inductance L. This is one of the major problems in the LC circuit. But Q is the same as in the series circuit, hence the Q factor is known as Q equal to 1 by R into root of L by C, or omega naught L divided by R, which is equal to 1 by omega naught into RC. And Q factor value of RLC circuit, resistance, inductance and capacitive circuits. See, a tuned radio frequency receiver is a class of radio receiver that contains one or more tuned radio frequency amplifier stages accompanied by a demodulator circuits to collect an audio signal and typically an audio frequency amplifier. So the quality factor of an ideal series RLC circuit and for a tuned radio frequency receiver is represented by Q equal to 1 by R into root of L by C, or omega naught L by R, which is equal to 1 by omega naught into R into C, where the resistance, inductance and capacitance of the tuned circuit are R, L and C. The resistance of the sequence is greater, the lower will be the value of Q in the circuit. So for a parallel RLC circuit, the Q factor will be the inverse of the series RLC circuit. So Q equal to R into root of C by L, or into R divided by omega naught by L, and it is equal to omega naught into R into C. So imagine a circuit where R, L, C are all parallel. The lower the parallel resistance, the more effective it would have on the damping of the circuit, and thus the lower the Q, this is the useful in filtering design for bandwidth determination. Next, in the Q factor for transfer function. So the filter response can be represented by the S domain transfer function. The parameter S comes is obtained from Laplace transformation and it represents complex frequency filters, also have a quality factor Q, and it is often expressed as alpha. So alpha equal to 1 by Q. This is commonly known as the damping ratio. Epsilon equal to 2 alpha. So the filter response can be represented by the S domain transfer function. The parameter S comes is obtained from Laplace transformation and represents the complex frequency filters, also have a quality factor Q, and is expressed as alpha. Here alpha equal to 1 divided by Q. So the Q factor of a low pass filter is defined by H of S equal to K divided by 1 plus S by omega naught. So this transfer function is the mathematical explanation of the frequency domain action of the first order low pass filter. The same transfer function can be expressed in terms of quality factor and omega naught also. So this H of S is equal to H divided by S square plus omega naught S divided by Q plus omega naught square. Here H naught is the pass band gain and omega naught is the cutoff frequency. And the Q factor of the high pass filter, the numerator of the low pass filter's transfer function is changed to H naught S square. The output of the high pass filter is similar in form to the low pass filter but flipped in frequency. So H of S equal to H naught S square divided by S square plus omega naught S divided by Q plus omega naught square. And Q factor of a band pass filter. So the numerator of the low pass filter is changed to H naught omega naught into S square to obtain the band pass filter function. So H naught is here as the H by Q, and in the band pass filter design Q is known as selectivity of the filter. So Q equal to F naught divided by FH minus FL. So FH and FL are the frequencies where the response is minus 3 dB from the maximum.